Hi. As you said, I work for Arxan. If anybody has any questions at all during the talk, just go ahead and speak up. Stop me if you have any questions about what's on the slide as well. This is a bit of a vague. I struggle a lot with this topic because, like, trying to find a name. But essentially, it's a lot of detection, which is the signature analysis part for malicious code or any code. And the software validation part is, hardening and resilience of binaries. So, get into this here. So, what is a signature? This is the biggest thing that I struggled with at first as I got into this research. And if you ever try to research signature analysis, if somebody comes up to you and says, "Do you want to do some research on this?" either know what they're talking about at first or say no, because there's way too many topics about signature analysis out there, and they're all completely different. One of the dictionaries online has a signature being a distinctive mark, characteristic, or sound indicating identity. If we're looking for malicious code, obviously a sound isn't going to help us a lot. Distinctive mark, maybe, but characteristic is what we really need to look for. So some kind of a behavior that is represented statically. So typically, signatures are signals when you think about computer systems. What you really need to think about in this is what a signature is. A signature is something that represents something else. And for the second point, we have a very specific definition that's related to the control flow of machine code. Because since this is binaries, we can't just look at the source code, right? Because we don't have the source code. And so, a signature for the purposes of code detection, malicious or not, then needs to be something representing a desired behavior through static analysis, as I said before. Therefore, defining a signature as a unique string of machine opcodes gets us what we want. Because a signature for malicious code is just code. So it's really pretty simple once you think about it, but it takes a while to come to that explanation. So a signature in this case would be, a push, move, move, sub, move, push, push, call. That is a signature. Because of the nature of machine code and its structure, searching for the string of instructions just in some binary is insufficient. You can't just load up, a hex dump and say, I'm going to look for these different code. Because you have jumps that go other places, you have other things that can affect it. So you really need control flow analysis in order to do this. If anyone isn't familiar with control flow, I'm going to go over this quickly. Control flow graphs and analysis. You can separate machine code into what's called basic blocks. So essentially, the idea, you can get into this second point as a definition, but the idea really is if you go into the basic block, you know for sure that you're going to execute every single instruction in that basic block before you leave it again. Right? So anything that jumps into it, that's going to start a basic block, and jumping out will end it. So, right. So anything that is executed prior to the current basic block, you can call it X, would be a predecessor after a successor. You can treat the basic blocks as nodes and then create directed edges to create a control flow graph, which gives you a full idea of how exactly the program flows and where your code is going to go in any situation. That's a crazy looking control flow graph. Right. So it gives us the outline of every possible flow of execution. If you can apply a signature by checking the control flow graph, you can assure that you check every single possible way that code is going to be executed. Now you could have dead code that doesn't get linked, that doesn't get run, but if that's the case, it's not going to matter anyways, But this gives you every single possible way that could happen. Problems with control flow and signature analysis. No-op equivalent instructions and groups of instructions, aka instructions that don't do anything but are just there to trip up your signatures. You could have, push A, pop A, and that doesn't do anything, but it is not in the signature and therefore will trip it up. This can be alleviated, though, as we'll talk about later. The biggest problem, especially with control flow analysis, is this guy. This computed jump issues with control flow analysis. It's a big vicious circle, and if any of you guys know how to solve it, then you'd make lots of money because it's really, really complicated. And so essentially you need data flow analysis, which we'll talk about later as well, in order to solve the computed jump problem, which is, I'm not jumping to an address, I'm jumping to whatever's in this register plus some other register plus some memory number or something. So, unknown from the analysis. Something that's only known at execution time. You need computed jump solutions to have full control flow analysis. However, you need control flow analysis for data flow analysis. So that's your vicious circle. There's no one has figured out how to solve it yet, but there are leaps being made. And you can kind of, if you know what the binaries are compiled from, you can make some good educated guesses. So how do we do malicious code detection? Create a list of signatures representing what you want, some virus, some this thing skips this code, whatever you got. Use signature analysis to detect it. We now know where the code is, but how can we analyze what it might affect, which is the next topic. Take a little side detour here. The signature analysis was my work specifically. The code slicing analysis is the work was done by the Wisconsin University, and you can go to this website and there's lots of cool slideshows and different things that you can look at, and it's all everything that they've done, all the work that they've done is to the public. So, right, and the people who actually did the work on code slicing in my group were my colleagues Chris Staley and Joseph Bateman. So if you have any questions for me that I can't answer about it, I will redirect you to them and they'll be able to help you out. So, right, so what is code slicing? It's pretty cool, actually. This first bullet, a code analysis method to determine which parts of a program may affect, which is a backward slice, or going backwards in the program, or be affected by a forward slice, variable values at some point of interest. So you have your big executable, you've done all the things that you need to do. For code slicing, if you say, pick some random instruction, some add instruction, and you say, I want to do a forward slice on this add, then code slicing will precisely give you every single instruction that is affected by that add instruction in execution. So, code slicing is an application of graph theory, and we all know that CS people love graphs and that there's nothing they can do to get away from them. So it starts with a control flow graph, which we've already looked at, which we just looked at for signature analysis. The next milestone is a program dependence graph. Code slicing for PDG is made up of flow dependence and control dependence graphs. So program dependence graph is a graph that's made up of two subgraphs. It allows intra-procedural slicing. So if you do a PDG on some function you write, printf or whatever, you wouldn't write that, but then you can figure out exactly which of these instructions will affect other instructions in that procedure, but you cannot do it throughout the whole program.